So to start off with, this is a result of the work done by the USGS National Water Quality Assessment Program. I do the trend analysis for the groundwater program. So that's what you're going to be seeing today. And to start off with, I wanted to explain how we got the network that I'm going to show today. In the time period of about 1992 to 2002, the USGS sampled 289 networks across the country. Each one of those dots isn't a well, it's a network of 20 to 30 wells. They could have either been domestic supply wells, which were representing the general aquifer quality, or shallow wells representing agricultural land use, or urban land use, roughly about a third of each. In the time period between 2002 and 2012, we went back to 67 of those networks, and we sampled again. We call this decadal sampling. Now, we've done some other time series work, but this is the main data set that we have to characterize groundwater quality changes over time. In addition, you're going to see today, we've continued this network from 2012 to the present. There's actually 26 networks that we're back, and we've seen the third round of sampling. So now we're not just talking about 2 data points, we're actually looking at 3, and it gets to be a little bit more interesting then. So we wanted to display this information to the public and show what contaminants were changing and how. And we developed a website that's interactive. It just was released a couple of weeks ago. Maybe some of you have seen it. And that shows the decadal scale changes in groundwater quality. Now, we sample for literally hundreds of constituents at almost every well. And we had to decide how to determine which constituents made it onto the map. And what we decided was we would map contaminants if they exceeded the maximum contaminant level, the secondary maximum contaminant level, or the health-based screening level in at least 1% of the wells nationwide. In addition, many of the organics did not meet that criteria. They typically don't exceed those standards. So we included the top 5 pesticides and the top 5 VOCs based on detection frequency. So before I get into the agricultural side of it, I would like to point out that most of the contaminants on that list, there's 24 of them, were naturally occurring. There were a few of human-related contaminants that we're going to talk about. And I'm going to spend the most of the time talking about this mapping tool. This is the map that will come up when you see it. I'm going to show you basically how it works. You have a selector here, and I'm going to start with nitrate because that's what we're kind of focusing on. On the map, you can see arrows and circles, and essentially what you can see is large increases, small increases, the black dot is no change, and then you have small decreases and large decreases. For every constituent, the relative size of that arrow is based on the relative change of the median of that network compared to the standard. So for nitrate, we're talking about 0.5 milligram per liter change in a decade is a large change. Smaller than that is a small change. And again, you can see there's a lot of black dots where there's no statistically significant change. When we look at these networks, there were 1 in 4 networks in agricultural areas that had increasing nitrate concentrations. That is a higher rate than for the domestic supply wells or the urban wells. That's not the case for every constituent. I'll mention when we get to some of the others. There are some other issues going on. What I did want to focus on, though, is what do we know about these changes in networks? There's a few of them here that I have circled. These are agricultural networks where we saw a change from the 90s to the early 2000s. These 3 in particular, we've revisited again, and I want to talk a little bit about what we saw there. So this is the map. This is not online yet. This is something very recent data. And we see these same 3 networks. And the one in California still increasing. The one down there in southern Georgia still increasing. But we saw a significantly and large change in this area up in Wisconsin. And this is the kind of thing we've been hoping we would see in networks around the country. We very rarely do. We don't always get a chance to zoom in and look at why we're seeing these changes. But we wanted to try, in this particular case, to see if we could see something. Before we talk about that, I want to put into this the context of lag times and how the changes that we're seeing might be affected by the way a specific well or a group of wells act. If we have a 25-year release of a contaminant over time in an aquifer, you might see a well like the one in the blue line that goes up very quickly, and then as soon as the contaminant is taken away, it decreases quickly. This would be typical of a shallow well. But we also have some wells where you see the contaminant rise very slowly in concentrations. So when we're looking at these results, we have to kind of keep in mind this context. Are we looking at a system that reacts very quickly or possibly very slowly? Let's say we sample in these two time periods, one during the time when we have the contaminant present and one later. Well, we look at this network and we say, oh, we took away the contaminant concentrations went down, that's exactly what we expected. But then you look at this particular network and you say, wow, what's going on here? We did all this work, nothing's happening. You have to consider lag times. And so as we look at this, that's one of the things we have to consider. I want to put that in context with one of the networks, the one that decreased. This is one that's in Wisconsin, and it has a very high median. You can see in 2002, the median was greater than 10 milligrams per liter in this network. But from 1994 to 2002, there was a statistically significant increase. From 2002 to 2014, there was a very significant decrease. So again, that caught my eye, said I'd like to look at this a little bit more detail. You can see we have a little bit of data that are biennial samples of these same wells, and that didn't really tell us a whole lot because they're kind of going up and down. What I did find is some data on fertilizer usage in Wisconsin, and you can see there's a fairly significant drop-off of fertilizer use. Unfortunately, it was down when concentrations were up. So that's where we go back to this concept of lag time. We do have some groundwater age dating data for this network, and a lot of the ages are around 10 years. So if you take this blue curve, which is fertilizer use, you'll notice that around 2004 or so, about the time when ethanol became highly used again, the corn production went up, nitrogen use went up. I think I talked to Kevin about this. He said this wasn't an unreasonable assumption. This isn't a detailed analysis, but if you just take this curve and you move it forward about 10 years, you'll see that that one really nice network that happened to decrease may well be going back up again if you look at the source of nitrogen in that. We don't really know this for sure, but this is the kind of things that we are doing. We also do mapping and modeling studies, which will really help us understand this area. We have a detailed study going on in this area. Another constituent we looked at was orthophosphate. You can see there's a fair number of networks with increases in phosphate. A lot of people kind of assume that's not going to move very much in groundwater. There are changes in a lot of these networks, not only agricultural networks. There's a lot of the urban and the domestic wells that had small changes in phosphorus. So this isn't just an agricultural issue, although we do think that there's some places where there's enough phosphorus that's built up in the soils that it is starting to break through from agricultural issues. Chloride and dissolved solids, my next two slides, these are equally bad in agricultural areas, urban areas, and domestic wells. And particularly if you look at the Northeast and the upper Midwest, those urban areas especially, there's a lot of road salt application and things like that. But if you look further west, a lot of these places that are irrigated agriculture, you also see increases in chloride. The dissolved solids slide looks very similar. And again, as you go across the country, there's different reasons why you have salinity issues, but essentially there are, this is one of the bigger problems we see. We're not talking about a couple of milligrams per liter change. We're talking about a network where the median changes 20, 30, 40 milligrams per liter in 10 years. And so these are some fairly high changes that we're seeing. We also looked at atrazine. Atrazine is the most frequently detected pesticide that we have. I think it's the most highly used pesticide in the country. And interestingly enough, atrazine concentrations were decreasing in 1/3 of the agricultural networks. So that's good news. And one of the reasons that we think differently about the pesticides is because there are substitutes for different pesticides. There are different formulations that come in and out of favor. The usage rate of atrazine has decreased over time. If you look at the amount, it kind of plateaus in the 90s, but the amount per acre has decreased. So instead of using all atrazine on a field, they'll use atrazine as 1/4 of a mixture with 3 or 4 other pesticides. So it's not entirely surprising. Unfortunately, there's no substitute for nitrate. So nitrogen is used in the same amount that it always has been. When we look at deethylatrazine, it was interesting. Some of the networks that were decreasing with respect to atrazine, deethylatrazine is one of the main breakdown products of atrazine. So some of the networks that were decreasing with the parent product were increasing with respect to deethylatrazine, which is the breakdown product. So especially in deeper wells. So we think that what's happening is the atrazine may be moving deeper and also being transformed as it goes deeper into the system. When we're looking at these data, there are several things that come to mind, and we've seen some other talks that have more detail than this. These 67 networks form the basis of our broad general understanding of water quality changes nationally. But we want to know more about short-term and seasonal variability. If we have a point here and a point here, and now a point here sometimes, we want to know what's going on in between. That's very important, because we might be seeing something that we just happen to hit hydrologic conditions that were different. What we've done about that is we've developed a network called the Enhanced Trends Network. And what that is, it is a series of wells. We have 8 networks across the country with about 3 wells each. Some of them are public supply wells that are pumping continuously. Others are monitoring wells. And some are even domestic wells, which are a little tricky to instrument. But what we do is we measure daily specific conductance, DO, pH, some field parameters, and water levels. And then in some cases, we actually have continuous nitrate monitors on these wells. And from this, we're trying to get an understanding of that variability on the daily scale, how these systems respond to wet and dry years, seasonal changes, so that we can put these larger networks that we're only able to get to every 10 years into a better context. And in addition, we can see what may be driving these changes. Some of these we have in areas that we have very good detail on fertilizer use in the fields around it and things of that nature. So we're hoping to get a better understanding of these decadal changes by understanding the short-term changes as well. On the other end of the scale, what about changes that have happened over 10, 20, 30, 40, 50 years? This is another part of the study. We call them the vertical flow path studies. Karen Burrows actually leading this. And so this is where we're just basically looking at depth, and we're looking at concentrations and time. And so from reconstructing the age concentration relationships, we can essentially look back into the past and understand how we got to where we are now and how contaminants are moving through time and through age, and what transformations might be happening over that time period. And so last of all, I wanted to point out this website is a new website, just came online. The URL might be a little bit complicated to write down, but if you go to the NAWQA website, it's one of the featured programs there. You can find it there. And all of the maps that I showed today that were of the 88 to 2012 data are on there. And hopefully within the next year or so, we'll get the more recent ones online as well. Thank you.
Thanks, Bruce. Lots of hands. Where do I start?
Johnson, Fresno State University. About how many wells in one network, and also how large an area the network covers. And lastly is, how did you determine the network?
I'll start with the first one. The networks were determined, the actual well locations. We had a random sampling grid that was overlain over a aquifer, sometimes a specific land use. We defined the study area, and then we typically overlaid a grid of 30 cells on that. So all of these networks started out with about 30 wells. And because it's a matched pair test we're doing, if we did not resample the same well, we don't use that in the statistical analysis. So through attrition, some of these networks are down to 20. So it's between 20 and 30 for most of the wells. And I think I missed your middle question.
How large an area that the network covers?
That's extremely variable, because some of these are urban areas that cover, for example, the Minneapolis-St. Paul urban center. And then there's others like the High Plains Aquifer, which cover a very, very large area. If you go to the mapper, the arrows show the network location, but you can click on that and zoom in, and you can see the distribution of the wells themselves. So you can answer, for any given area, you can see how large of an area was covered.
Hi, Bruce. You mentioned that you will have some do some monitoring to map out the seasonal variability of the nitrate water parameters. Is this just a thought, or do you have some results now from those monitoring?
I don't have those results yet. I think we're going to try to publish them as soon as we can, but we don't have them yet.
Yeah, great talk, Bruce. You probably know where I'm going with this, but did you look at the thickness of the unsaturated zone in the boreholes as well to try and look at the lag times?
We have, again, if you go to the map, there's a lot of details on there, and you can't easily separate it out, but you can zoom into any given network and you can see the range of well depths on there. So some of these are fairly deep and some of them are shallow. You could probably piece together from looking at the map and then looking at the well depth range if there was a relationship between that. Typically, you're going to see more variation in the shallow quicker than you would see in the deeper zones.
Okay, thanks.
Hi, I have a question about the comparability of the data throughout the years. In the Netherlands, we sometimes have difficulty when, for instance, different provinces sample groundwater wells, that they use different methods for sampling. For instance, the speed with which they subtract the water for samples, and also they can use different labs to do their analysis. And especially with pesticides, this can be have different accuracies. And I was wondering, because this sounds like a huge database, if you can say anything about the comparability of the methods throughout the years and the locations.
Thank you. We use one lab for everything. So we are fortunate in that we have the National Water Quality Lab that does all of our analysis, and any non-standard, like some of our radiochemicals, go out to other labs, but they're always the same. So the vast majority of these went to the same lab. We also have a training course. Everybody who goes to the field to collect this data has been to a 2-week course in Denver to learn our methods and our way of doing it. And so there's a protocol that we all follow for data collection. So as much as possible, we try to eliminate those variables.
Okay, thanks a lot, Bruce.
Thank you.